Hi, everybody. What we're going to do today is do a little presentation here about density. I think this is a topic that you've had previously in general science, so hopefully it should be a review. If not, remember the density video that you watched, and also there are sections of density in your textbook. What we're going to really work on today is problem solving with density. Okay, so we'll do a quick definition and then we'll work on some problem solving. So here's the definition of density, the mass per unit volume of a substance. And you can see that that translates into a little equation there, okay, where D is density. You'd have to have some kind of mass unit like grams or kilograms divided by a volume unit like liters or milliliters or centimeters cubed. And that density is equal to mass, and mass is going to be divided by volume. Okay, mass units are things like grams, kilograms. Volume units are things like liters, milliliters, centimeters cubed. And obviously your units on this side have to equal your units on this side. Okay, like if the density is in grams per liter, then you got to put your volume in liters. It is an intensive physical property. Intensive means it does not depend upon the size of the sample. For example, if you have 2 cups of water instead of 1 cup of water, you do have double the volume, right? I'm having a little trouble writing because I don't have my best pen here. But you also would double the mass. And so those twos kind of divide out and you get the same mass to volume ratio. You could have a bathtub full of water and it's still going to have the same mass to volume ratio. It's a physical property because you can measure the mass and the volume without changing the substance at all. So they're just physical measurements that you take and the substance retains its own identity. So for the reason that it's, physical property and intensive, doesn't change with the sample size, it's really good for identification, and we'll try and use it like that in the lab. So here we have a sample problem, okay? And gold is very dense. That's why when they would pan, the gold would sink to the bottom of the pan and they could swoosh everything else out with the water and retain those gold nuggets on the bottom. But if you're trying to determine the mass, you have to take your density equation, okay? I'm going to struggle a little bit today because I left my pens somewhere else. All right, there we go. And we have to take the density equation and we have to rearrange it to solve for the mass, which means that we can multiply both sides by volume. So if we have density times volume, that's going to equal the mass, because over here they'll divide out. Now you got to make sure your units match up. If the density is in grams per centimeter cubed, then my volume has to be in centimeters cubed too. We know that milliliters is the same thing as a centimeter cubed, so I'm just going to trade out that unit. And you can see then that the centimeters cubed divides out, and that gives us an answer in grams. And when I multiply that, I got 86.85, but I'm going to round it to 2 significant figures. When you're doing the sig figs, the density is a constant. So you don't want to use that to limit your sig figs. You want to look at this number, and 4.5 has 2 sig figs. So I'm going to take that 87.85 and I'm going to round it to 87, and grams is the unit. Don't mind that little random line going through there. It's a little hard to write sometimes on the screen. Okay, how about a problem like this? I literally took a silver bracelet one time and I weighed it. And I was able to, by water displacement, okay, kind of see if this calculation worked out, and it does. And we know that if it's made of pure silver, the density is 10.5. So what volume would I be expecting? Well, remember, density is mass over volume. So we rearrange that. Density times volume is mass. And then I need to get the volume by itself, so I'm going to divide both sides by the density. So we can see that volume is equal to mass divided by density. In this case, my bracelet weighed 32.5 grams. And the density is 10.5. When you divide, the grams cancel out. And in the units, follow me here, you're left with 1/1 centimeters cubed. Do you guys remember how, like, you take the fraction on the bottom, you invert and multiply? That means that's your label. And when I divide this, I get 3.0952, et cetera, et cetera, et cetera, a bunch of numbers. The density, this is a constant, but I'm going to use the 32.5, 3 sig figs, and I'm going to round my answer to 3 significant figures. 3.10 centimeters cubed. And when I put that bracelet in a beaker, it was about 3 milliliters of water that kind of went out over. I poured it into a cylinder then to kind of verify that. Now, what if an object has a regular shape? Okay. There are, for example, cylinders, cubes, cones, spheres. Okay. If an object has a regular shape, you can use equations that you've learned in math class to determine the volume of that object. Okay. So here, for example, we know the cylinder is pi. Now remember, r is just half of the diameter. So it has a diameter of 3. So the radius is 1.5, and you got to square it. And then the height of the cylinder is 6.0 centimeters. And so notice here you got centimeters squared times centimeters. That's centimeters cubed. That's going to be milliliters. So like if we did have the dimensions in some other units, we could put them in centimeters. And then when we put them in this equation, we'd come up with the volume in centimeters cubed, which we know is milliliters. And to solve this, we've got to take the 1.5 and square it, multiply by pi. If you don't have pi on your calculator, use 3.14, and then multiply by 6. I got 42.41, but I'm going to just round that to 2 sig figs. And then we know that density is equal to the mass. It says right here, the mass, 117.00 grams, divided by the volume, which we just calculated. Now the volume has 2 sig figs, so when I divide this, again, I got a long decimal number, but I'm just going to round it to 2 significant figures. And then my units are grams per centimeter cubed, or grams per milliliter. I could do this with any kind of regularly shaped object. I might give you problems for cylinders where you would use this to find the volume. If it's something that has a rectangular shape, like a long brick kind of shape, then you might use the length times the width times the height. And if they're all in centimeters, then you can get centimeters cubed, which is the same as a milliliter. Or if it's a big object and they're all in decimeters, then you could get decimeters cubed, which is liters. And then if it's a cube, you just take the length of each side. Length, width, height, they're all the same. So you take the length of a side and you cube it. You see that no matter which one of these you use, you're going to come up with some sort of cubic distance. Cubic centimeters, which are milliliters. Cubic decimeters, which are liters. And you can use that then for the volume. Now, I won't expect you to know like a sphere or a cone or anything, but you could always look those equations up if you needed those. Okay, but what about the object that does not have a regular shape? Think about like that bracelet. That bracelet was kind of awkward. I had to put it in a beaker of water and see how much water came out over the top. But in lab, we'll try to use a graduated cylinder where our object, we can fit it into a cylinder of water, and actually do measurements and see how much the water level goes up. Okay. And for this to work, the object has to like not react with or dissolve in the water. Okay. So that's kind of a requirement. If it reacts with water, sometimes I've seen displacement of like cooking oil or something because maybe it won't react with that. And it also has to be completely submerged. If any of the object is sticking out the top, that means it has not displaced water and would not get measured. So let's just try one quick, if I can get my slide to change. There we go. Let's see. Water displacement. And then here we go. So if I have an irregularly shaped object, there's the mass, 16.40 grams. If it's put in a graduated cylinder, there's 20 milliliters of water, and the water level goes up to 22.3. To get the volume of the object, you have to take the new water level. Oh goodness, my pen isn't so good there, is it? Sorry. That's 22.3 minus the 20, and it's 2.3 milliliters in this case. And then to get the density, it's mass divided by volume. Not the volume of the water, not the volume of the water and the object, just the volume of the object itself. And when we divide, we're going to get here 7.1 grams per milliliter. Now again, I got 7.1304, like numbers, but I'm using my sig figs. Every once in a while, people will look at this and they'll say, well, these have 3 sig figs, but remember the addition and subtraction rules. We can only keep this to the 10th, and this new number has 2 sig figs, which means 2 sig figs in my answer. And this is the density. Now, when you're doing problems, watch the units. Like if the mass is in kilograms and the density is in grams per milliliter, you've got to convert the kilograms to grams so the units match up. But we'll get you doing some practice problems. And hopefully you can manipulate that equation to solve for any one of the variables. If it's a regularly shaped object, you've got to use those equations like the volume is pi r squared times height for a cylinder. And if it's an irregularly shaped object, you got to use water displacement like we just did in the last problem. So good luck. Hopefully you can have some good luck solving some of the density problems. Okay. And be sure to ask. You can always come in during Flex if you need a little help with any of them.